As a brief overview, as you know, NIRSpec has multiple science modes. So it can take spectra, it can take low resolution spectra using the prism between 0.6 and 5.3 micron, medium and high resolution spectra using gratings between 0.7 and 5.2 micron, so directly adjacent to MIRI. And all spectral modes are available for fixed slit spectroscopy, integral field spectroscopy, and multi-object spectroscopy with the microshutter array. The IFU has a field of view of 3.1 times 3.2 square arc seconds. And the MSA covers a much, much larger field of view of 3.6 times 3.4 arc minutes. But as we'll see, with gaps in between due to the chip gap and the microshutter quadrant gaps. And this is on the left. You can see a sketch how NIRSpec actually looks like. And the good thing is NIRSpec is an all reflective instrument, which makes the throughput actually really, really high, like close to 90%. So this is a sketch how spectra map on the detectors. And I'm just showing this because this is important to understand the rest of this presentation. And here on the left, I think you can see my cursor. Anyways, on the left, you see those small blue squares. Those are the microshutter quadrants. So there are 4 individual quadrants, each of about 370 times 350 shutters, which makes in total a 250,000 of shutters. And you can see those quadrants have gaps. And then on the right, where you can see the spectral traces, you can see those are the 2 NIRSpec detectors, NRS1 and NRS2. And depending on where your sources are relative to the microshutters, which are the red dots in those little blue squares on the left, that determines where your spectral traces actually fall on the detector. And you can see that also depending on the trace length, some of the spectra or parts of the spectra actually fall off the detector to the red end. So it is quite important to also, especially for the MSA observations, to plan accordingly to this. And the only mode where you can fit multiple objects in the same row so that the spectra don't overlap is the prism mode, because the prism is actually short enough due to the low spectral resolution. And additionally, we have some features, especially the age gratings. You have second order contamination on the red end, which is indicated on the top by the green line. Then, of course, you have the detector gap, which depending on where your source falls, your spectrum will have a gap. And also some of the spectra, you can see those zero order contamination, which you have here indicated is this red square, but this is typically not that big of a problem for normal spectra, since there's nothing falling here. And those are always falling on NRS1. So at first, I will talk a little bit about this NIRSpec parametric model. And if some of you already have observations or plan some, you probably have heard about this. And the big thing is that NIRSpec is a very complicated instrument with those various observing mode, slit apertures, spectral resolutions, and the microshutter array. It also depends on where your object falls relative to the detector, which means it is impossible to every time take dedicated calibration for each of the observations. It will simply take too long, and also it's computationally too complicated. Because you have, as I said, those 250,000 of individual shutters, you have those multiple gratings, limited angular position and reparability of the grating wheel assembly. I will come to this later. So basically, every time you turn the grating wheel by, let's say, 360 degrees, you're not ending up at the exact same position, which causes small wavelength changes relative to the position on the detector. And since the field of view is so large, also distortions, and it's important to get an accurate astrometric solution. So therefore, we developed a instrument model which is an end-to-end simulation of the optical path. And then during commissioning, we used internal observations and on-sky data to actually fit about over 900 parameters, which then can simulate now perfectly the optical path and is used actually for the calibration. And there are like three main parts, which is the FORE optics and the optical telescope element, which is like this part, which is fitted with on-sky data of the astrometric field, which is a dense field in the Large Magellanic Cloud. Then the spectrograph itself, which we calibrated with internal lamp exposures, and then, as I said, the grating wheel sensor calibration, also to actually know where to end up when turning the wheel. And the spectrograph model was basically the internal one, where we used internal lamps to first see where traces actually fall on the detector, depending on where your source lands in the microshutter array. And then we also have wavelength calibration by those absorption emission lines from the internal lamps, and to calibrate the reference points and basically the 0 points for the wavelength calibration. Then to fit those, the second step was the FORE optics. So we used the astrometric field, which you can see here on the left. This is NIRSpec in imaging mode. So all shutters are open and no disperser is in the optical path. So you get actually a fairly nice image with a lot of, you can see all of the defects of the microshutter array. But in the end, you can actually measure the positions of the stars on sky to get the astrometric solution. And this was done by a least square fit by modeling the PSF throughout the field of view. And you can see here, it looks not as nice as of course, an imager, because you have the shutter bars in between the microshutter array. And last but not least, as I said, was the limited angular positioning of the grating wheel assembly. And to counteract this, there are sensors in that array that basically that give out a voltage depending on where the grating wheel is. And we spun the grating wheel, observed, and then looked at the voltage and basically calibrated so the voltage with the grating wheel angle. And this is like the example for the G395M calibration. So all in all, this procedure in commissioning took us about 6 weeks. That's also the reason why you can't do this on the fly. And so in the end, the internal spectrograph calibration is accurate to 1/10 of a resolution element or 1/20 of a pixel for all modes and gratings. The astrometric solution ranges depending on the filter between 0.1 and 0.25 pixels, which is slightly larger than we know from ground, but a lot of tests showed that this is actually not caused by the astrometric solution, but rather the centering algorithm due to the shadow, the bars of the microshutter array. And also the grating wheel is again below the 1/10 of a pixel, which was then success. So as I talked, the microshutter array, this is how the thing looks like. So you have the 4 quadrants. In between, you have the IFU aperture, which is this larger square, and then you have your 4 slits in between, which also means the traces of the slits never overlap with the traces of the microshutter array. This is different to the IFU, because even though the IFU aperture is here, the IFU maps on the same region as the microshutter array. And this will become very important when we look at this. So this is how the microshutter array actually looks like currently, with all its defects. And you have here the vignetted shutters, which are basically the microshutter array is a little larger than the actual field of view. So some of the shutters around are vignetted. And even though you can operate them, you can't map them on the detector. Then you have those failed open shutters, which are marked by these little red circles. And that's where it is important that the IFU maps on the same region of the detector, because if you have a dense field, you will always have contaminating traces due to those open shutters, because as the name is, you can't actually close them. So that's why it's also important to dither IFU observations to get your source at different positions on the detector, so that you can actually remove those traces or the contaminating traces. Then we have quite a lot of failed closed shutters, which are all of those dark little rectangles. Those are shutters that we cannot open. They're not operatable for whatever reason, but they don't open. I mean, that's the only thing we know. And in addition, we have short masks. I come to that a little later. And to mask, so shorts are, I can also mention, now shorts are basically, for shorts, we need to turn off either the whole row or the whole column. And this is why you have this cross pattern here. So you lose always the whole row. So in total, we have about 82.5% of all shutters are usable, and the total failed open are currently 22. And this is actually still low enough that it does not really affect the multiplexing capacity of NIRSpec. So with dithering and everything, you can actually work around. So the multiplexing is not it's not influenced by those shutters. So you're not losing a lot of science. And during commissioning, we also tested more than 800 reconfigurations of the microshutter array. And from these, we determined that you have an average success rate of 96% that a shutter actually opens when commanded. So what that means is that if you point to 100 sources and you open 100 shutters, there is a chance that 4 of those 100 shutters may not open, and that source you can't observe in any given configuration. But yeah, it's nothing we can currently do about this. This is how it looks like. It's the same image as I showed before, and that's where all those dark areas are coming from. And this is how it then looks like dispersed on the detector. And there you can see that we opened nicely some slitlets, but you also have those contaminating traces from those permanently open shutters. And here you can see the 0th order and the fixed slits here in the center. And electrical shorts. So if you have already observed or worked with data, you may have heard of these, since they are actually still appearing. And it's basically that we have some contamination, and that creates literal electrical shorts between 2 rows or columns of the same, for example, of neighboring arrays, and of neighboring columns or rows on the MSA or within a shutter. And what this means is that you have a current you don't want it there, which you don't want there, which causes a glow on the detector. And they come in different forms and shapes and locations, which also means it's basically impossible to calibrate them out. And these are examples. You can have here like a glow or a double glow, or you can have a glow and some reflection inside the instrument. So you can see here on the top right, which is quadrant 3, you can see here literally the whole microshutter array illuminated basically from the back. You can even see here the pseudo slits of the IFU and also on the bottom. So as I said, they come in different forms and shapes, and that typically means if we discover them, we run a so-called short detection, which means we are turning off the row or column or both of where these glows appear. And then most likely your observations need to be repeated. So if you see anything suspicious like this, mostly we catch it when we do quick look for all of the data. But if you see something like this, you need to open a so-called Whopper, and we look into this. And most likely, if it's a short, most likely the observations need to be repeated since they're not really usable. And last but not least, a little bit about the absolute flux calibration, since this is something that people are desperately waiting for, and we haven't finished it yet, honestly, but we are getting there. And it's complicated. So for an absolute flux calibration, it's done in 3 steps for NIRSpec. One, it's the detector flat, which is the pixel-to-pixel response variations on the detector. And this is flat fielding as you're used to typical with like anywhere for like also imaging, which is a typical flat field of the detector. But in addition, we also have the spectrograph flat, which is from only the spectrograph part. Again, here the reddish part, which corrects throughput variations in the spectrograph. And this is done with internal lamps during flight. And then we also have the FORE optics, which we also need to correct for field and wavelength effects caused by the NIRSpec FORE optics, like the filter wheels and the telescope itself. And so far, the detector flats we have, those are still from ground. So they stand as they are. But for both the spectrograph flats and the FORE of flats, which are the SFLT and FFLTs, these analyses are ongoing. And if you have seen spectra from a few months ago, you saw that the units are basically off by a factor of 10 to the 12. And in the meantime, we delivered so-called hybrid files, which are simulated flat fields from like pre-flight knowledge, from like throughput and the spectrograph response. And with those, we can do flux calibration, with an accuracy of up to 40%. So it's not great, but it brings you into the right ballpark. Currently, we are working on the actual final, or like the real flat fields from like on-sky observations and from the in-flight orbit. And the first step is to get the spectrograph flats, because those are needed to get the FORE optic flats. So, and they depend on the disperser and the slit aperture. Oh yeah, what I forgot to mention, you can always check CRDS, which I posted here, the link. There you can always see the current calibration files for actually each instrument. So that is for the whole telescope. And why it is so complicated to get those files is because we need it for each mode, fixed slit, IFU, and MOS. And we need 2 reference files, one for each detector, and using the internal lamp exposures. And for the fixed slit and the IFU, those are done also with 2 parts. One is a 2D image, which is the pixel-to-pixel variations of the slits and slices. And the other one is a vector for each slit or pseudo slit for the IFU to correct wavelength dependent and fast throughput variations. And this is also mainly because the slits are not perfect. So they are not perfectly shaped. They are like, the borders are not absolutely straight. And for the MOS, the difference is that for the microshutter array, different parts of the spectrum or different parts can fall, or the same spectrum can fall on different parts of the detector. So each pixel actually receives light for different wavelengths. Hence, this is a huge data cube. And the FLAT works pretty much similar. We again have it for all of the modes. And that actually allows the conversion from like counts per second or photons per second to actually absolute flux units. And currently we are finalizing the S and F flat for the fixed slit and the IFU. So these we will deliver soon. The MOS mode is still work in progress. And these are preliminary results, or these are the results from the files we will deliver. So you can see on the left, this is the standard star HD 1808-34-7. And you can see here in black, that's the actual calibrated spectra. And in orange, which you barely can see, is the standard star from the standard star library. So they match very, very well. And the RMS residuals are below 5%. And more importantly, there's little to no wavelength dependence. On the right, we did a test with a star, which we observed early on during commissioning. And also that matches very well, even though the offsets here can be explained because at this point, target acquisition wasn't working. So we don't know how well centered the star is in the slit. These are the caveats. I mean, I also will leave this so that people can read through, can read it themselves. And it's also everything is on JWebs. But the most important thing is that NIRSpec, especially for the fixed slits and the IFU, we currently don't have aperture correction, which means we advise that you use as an extraction aperture, which is 5 pixels for the fixed slits and 4 spaxels or 0.4 arc seconds for the IFU, and to use these for the pipeline extractions. These are also the default parameters in the pipeline. But if you decide to use a different aperture, currently you have to do the aperture correction yourself. We will provide aperture correction, but this is part of the cycle 1 calibration problem. Also, currently, we only have had one standard star per observing mode, which means we don't have different stars to actually test it against, which means those calibrations are best case scenarios, and any systematic uncertainties we will introduce and we will show in the future when now during cycle 1, we will observe multiple stars. And yeah, so those are the main things that you should be aware currently. And as I said, though, we will improve this during an extended cycle 1 calibration program, including also like field dependence, like where your source falls on the micro shutter array and so on. And yeah, so that's it from my side.